All right, those last notes, we found volumes of solids where when we took a slice, every slice had the same shape face, and we were able to write an expression to use for the area of that face. Then we could write an integral that added up all of the volumes of those slices using this important idea from geometry that the volume of a prism is the area of the face times the height. So what we have here is actually a much more common problem if you're thinking about the AP test. It's really just a special specific case of finding a volume by using slices that have cross sections that all have this same shape. And that's going to be when we revolve a region around an axis. An axis is just a fancy name for a line that you spin something around. So imagine taking this, we've seen this before, this region R. We're going to pretend that it's held still on this red axis, and we're going to spin that region around the red axis. Well, since the region bumps all the way up against the axis, which in this case the axis we're revolving around happens to be the x-axis, if you did that, you would make a solid shape. There's going to be no spaces, no holes. If we wanted to then slice this solid, imagine taking a slice here, a slice here, a slice here. We could slice it into infinitely many, infinitely thin cylinders, right? So every slice would have a face that looks like a circle, but the slice would have thickness. So if we think of that as the area of a circle, pi r squared, times the thickness, we can find the volume of each slice. And it's just really a special case, like I said, of the integrals we had in the last video, where we're going to integrate the area as a function of x times the thickness of the slice, where area times thickness gives volume. So I've been teaching AP Calculus for a while now, and these steps here that I'm describing, I'm going to really strongly suggest that you try them, that you really get different colored markers or pencils and try this on the pictures. It will help you make connections to what we did in class today, where we were slicing up your bucket or whatever it was into infinitely many, infinitely thin cylinders and writing an integral to model that. If you had any moment during that project in class where you weren't sure what limits you should use, or you weren't sure exactly what your integrand should be, these steps using these colors will help you make those connections. And I think help you, like I say, avoid that time, that moment I had when I was in high school calculus where I was just trying to guess what numbers went in. I didn't really understand this idea of an integral to sum up an infinite number of volumes. So imagine that picture we had up above. I'm going to take this region R and spin it around the x-axis. I'm going to make a solid shape, and I want to find its volume. So here are my suggested steps. We're going to take that region R, and we're going to shade it in. So I'm going to use this gray color and shade it in. Now I'm going to draw the axis of revolution. I've been told that this curve is going to be rotated around the x-axis, so I'm going to use red to color in the x-axis, just the part that touches the region, just the part that's in between the x values I've been told about, 0 and 4. I'm going to reflect my shaded area over that axis, whoops, which I should do with gray. I just use gray because you probably just want to use your pencil to do it. It's not a big deal. If you have a different color scheme you want to pick, that's fine. This is the color scheme I'm going to use. All right. I could then shade that in. All right. I'm going to now imagine slicing this shape. It's a solid shape now, even though I only have 2 dimensions on my paper. So the idea, well, specifically, when we use slicing to think about volumes in high school calculus, so that's calculus A, B, and BC, we're always going to take our slices, perpendicular to the axis of rotation. There are other ways to find volumes that you could look up, that you might enjoy, that you might study in college. But in high school calculus, we're going to always slice perpendicular to the axis of revolution. So here, if I revolved around the x-axis, that means I'm going to have to take my slices vertically. The x-axis is horizontal, so I'm going to slice vertically. So I'm going to start my green pen on the axis of revolution. I'm going to draw toward the boundary of my original region. So my original boundary was this graph y equals square root of x. So I'm going to start at the axis of revolution. I'm going to draw toward the boundary. I'm going to draw it back around behind the axis of revolution and back up to meet. So that doesn't look like a circle because I'm trying to draw it with perspective. But if you imagine taking that slice out and looking at it, the face of the slice would be a circle, but the slice would have a thickness. All right, so I'm going to use my blue marker now to draw the radius of that green disc. Radius, it's the line that goes from the center of the circle to the outside edge. In order to help us understand the picture and what function we're going to have to put in our integrand, draw toward some kind of curve that was already a boundary of your original region. So the only curve I really have in this problem is y equals square root of x. So I'm going to start my pen in the center of the green disc, and I'm going to draw toward the curve y equals square root of x. Okay, that's my radius. That's what I need an expression for. All right, so I'm going to use horizontal or vertical distances to write an expression for the blue radius. The blue radius I drew in, it's a vertical line segment. So to find the length of it, luckily the place where it's the bottom of that radius is y equals 0, the x-axis. So all I need is an expression for the top. Well, that was not so bad. Here I can say the height of that blue line is always going to be the y value of that function, so y equals square root of x. So I'm going to write radius square root of x. Now I'm going to integrate pi times r squared times the thickness to find the volume of the solid. So I'm going to integrate pi r squared times the thickness. Well, the thickness of the slice, if I took it perpendicular to the x-axis, is a very, very, very small change in x. That's my dx. Now I can tell that I'm writing an integral with respect to x, which means my limits are going to have to be x values, the lowest and highest x value that my shading touched. So in this case, it's from 0 to 4. That's a 4. Didn't really look like a 4. My marker's so thick. 4. 4. And now I just have to fill my radius in. Here the radius wasn't so bad. It's square root of x. Again, that's a 4. So I'm going to hide this and simplify that. Radical. Okay, so now I'm going to take this integral and evaluate it. This should be the easy part, right? So this is the integral from 0 to 4 pi times, well, square root of x squared is just x dx. An antiderivative for pi x is pi x squared over 2. I'm going to integrate that from 0 to 4. So that's pi times 16 over 2, which is 8 pi, minus pi times 0 squared over 2, which is 0, which is just 8 pi. The volume of that solid is 8 pi cubic units.